Can you give us an update on what's actually happening on the metallization evolutionary approach to process technology?
Absolutely. As you walk around the stands today with DuPont and with many, even our competition, you will see on the big banners product numbers. And these are the products that have been sold into the market today. The example being DuPont PV16X series. This is a front-side silver metallization. And it's a product we've launched this year from the previous PV159. And we make these evolutionary improvements. What are the customers looking for when we do this? It's small electrical improvements. Electrical improvements directly translate into efficiency improvements in the modules and therefore reduce the cost per watt for the manufacturing costs. As you know, most of this industry is dependent upon the feed-in tariffs, so as the feed-in tariffs are reduced, it's most important that our customers are enabled to reduce their costs at the same time with the products they have in production, or shall we say with the production processes that they've already invested in. Because that's important. PV was very capital intensive to move toward from where it was, a few hundred megawatts, to where it is today, to several tens of gigawatts. And as we move tomorrow, so it's most important that you're able to utilize existing capital when you're giving them improvements. And that's
now that's obviously not just, as you say, with the metallization pace, but the whole sort of approach to where the direct improvements can be made in cell efficiencies via all the metallization process steps. How is DuPont working with customers to improve that side?
With the evolutionary type materials, we take these products into our customers, and it's most important at that point we teach the customer how to use them. So it's not usually so simple that they can put them in an existing process and it will work. We all wish this is true. This is the real world. Processes need tweaking, need optimizing. We have a tech service group in every market around the world, and they go into customers, and it's their job to take, for example, PV16A, PV16B into a customer, work with their technicians on the line, and optimize it for their particular processing. Because as you know, this industry was built upon turnkey applications, really, and so you had many, many similar processes. And then when a particular user got up to speed with the technology, his own scientists then were improving the process. So the real processes started to diverge as people differentiated themselves. So it's very important then when you introduce a new product, a new change, it's tolerant to this broad range of processes and you're able to go in and optimize them for that particular customer. And that we actually do very, very well. As I say, we have a large team worldwide and we train them extensively. And our customers, I think, trust the DuPont technical service people to change parameters within their process, go on the line and work with them side by side. And that has been one of our success factors.
Now, obviously, there's another side to cell efficiency improvements, and that's a more aggressive, shall we say, more revolutionary approach. What is DuPont doing in that field?
A very good question. And we're standing next to our technology roadmap here. And in the lower part of this picture, we can see the cell structure changes that we're going to see in the future. If you take an existing cell structure, there is a theoretical limit as to where you're going to get with it. And so you'll get on diminishing returns as you start to do developments in the future. So we need to change things. This is the revolutionary part. So we need to change things like we move the bus bars from the front to the back. Back contact cells, these are called, and that's great. But we can't do that on our own. We can enable the metallizations, but when you've got all the bus bars on the back, you need to have module manufacturers enabled to take those into new designs for modules. So this is going to be a revolution through the industry as you change the approach. That's one approach. We take one of the other ones, selective emitter. This is a very popular buzzword at the moment. Without getting into the technical details, DuPont Pace enabled the selective emitter to work. The selective emitter essentially creates a deeper emitter just below the fingers on the front side. PV16A has been shown to work in many, many of the processes that are around today.
Is there also an attraction with selective emitters that you can actually, you're customizing the paste for the two different criteria that is required, and that gives you a much tighter tolerance on the process.
You're absolutely right. The selective emitter approach moves the industry to starting to fine-tune individual parameters on the cell. Previously, if we went back to no more than 5 years, we're talking about one paste almost should do all. And clearly today, as we go to shallow emitters, selective emitters, similar type of technology, that's exactly what you're doing. You're fine-tuning that paste that's making contact to the fingers above that selective emitter section. And that's quite a different technology challenge than if you're trying to put a busbar down. And if we were to go on and talk about other technologies like metal wrap through, that takes your point probably to the extreme where you're totally decoupling the fingers from the busbar. That's great. You're leaving the fingers on the front side, and they have all the properties you need to make good electrical contact with the PN junction. But you're taking that busbar and you're putting it on the back, and you don't need it to fire through and make a good electrical contact. Now it's not one paste fits all. You're customizing the paste to optimize the process.
All right. Well, obviously, always the challenge in this industry when you're looking at more revolutionary processes and technology advancements to gain, to achieve greater cell efficiencies. Can crystalline technology still remain competitive with those conditions and advances compared to something like thin film technology?
Yeah, another good question. As we came through 2008, 2009, clearly there was this big divide between crystalline silicon and thin film technologies. And I'm generalizing about thin film without getting into the individual technologies that are probably more cost effective, but let's generalize for the moment. As we came through 2009, and there was essentially a cost crash in the industry, and then as we go forward, crystalline silicon has become so much more competitive than it was before, and it's really challenging thin film, to the extent that with these revolutionary changes we're talking about in technology, which, let's remind ourselves, are aimed at reducing cost, $1 per watt at the end of the day. With all these changes implemented, you probably be very, very similar in cost of ownership, if you like, for thin film and crystalline silicon. And in which case, I still believe crystalline silicon will be the dominant technology for many, many years to come.
Is there not just a roadmap, but when do you expect to see mainstream volume production of some of these more advanced technology, crystalline cell technology coming out?
Yeah, it's all commercial. It's all driven by commercial parameters, as you would expect. Today we are reliant upon individual countries' feed-in tariffs, and clearly Germany has been a leader in that area. But as we move towards this idea of grid parity, it becomes commercially more attractive, or shall we say commercially less uncertain, because you're at normal market forces. At this point, the lower cost of ownership technologies that you're going to implement through your roadmap will naturally come to the top, cream to the top of the milk. And these will be technologies that will drive the big volume and capacity improvements for the future. But let's not forget, we will probably still have the current technology in many, many applications across the world. So we will then start to diversify quite a lot of technology around the world. But that's, I think, essentially what will happen. Grid parity is what we're all driving to, and that will drive or differentiate the new technologies.